Hello and welcome back to Classes with Atish. We'll continue with our lecture on waves. This is lecture number 2 and we will discuss plane progressive harmonic waves today. Okay? Okay. So if you have not already checked out the lecture number 1, I'd encourage you to do so. You'll find the link somewhere in the description below. And in that lecture, we introduced what is a wave and then classified waves and also talked about the general equation of a wave. Now, just as a quick refresher, the general equation of a wave, I'll write it right here, is y, which is the disturbance, is a function of ax plus minus bt. Okay? If a function is of this form, then it is a wave equation and y is defined for all values of x and t. As a further reminder, I would also like to put in those two conditions. Del square y del t square equals k del square y del x square, where k is not equals to 0 and obviously y is defined for all values of x and t. This is the partial differential equation. This is the partial differential equation of a wave. Okay? One of the solutions of this is the wave equation of a plane progressive harmonic wave. Let's first define what is a plane progressive harmonic wave. A plane progressive harmonic wave is one in which all the particles are exhibiting simple harmonic motion. Okay? Also do remember, we define waves such that wave is not one of these simple harmonic motion. It is a collection of simple harmonic motions of each and every particle of the medium. Okay? So this is what a harmonic wave is. Okay, let us try to draw a graph of y, which is the disturbance, versus x. Okay? Consider a string which is attached to the wall, and then I am creating some waves by introducing some motion to the source particle, and then a wave is created in the string. Okay? And then at some point I take a snapshot. So at some time I am looking to see the relation between the disturbance and each and every point on the string. X denotes each and every point on the string and y denotes the disturbance. Okay, so let's say we have a wave like this. All right, so at x equals 0 is the source particle where I started that disturbance, and the disturbance that was created here, it moved along the length of the string, and at some time I took a snapshot, and this is what I get. Now we can say y is a function of ax minus bt. Why I have taken minus is, as you have learnt in the previous lecture, if the signs of the coefficient of x and t are opposite, then the wave is traveling in the positive x direction, which is what we have represented here. Y is a function of ax minus bt, and we know the wave velocity we can get by coefficient of t divided by coefficient of x, so it will be b by a. Okay, and this wave is traveling in the positive x direction. Now, I would like to define a few other things. First is wavelength, the distance traveled by the wave in one time period. We denote wavelength by lambda, and this is the distance traveled by the wave in one time period. Okay. So if the wave is traveling with a velocity v, then what is the distance traveled by a wave in one time period? It will be v times t. Okay. And what is the distance here? It is this distance. Okay. The next thing is frequency. What is frequency? Frequency is the number of oscillations in one time period. Okay. So we can say this is or the number of waves that passes through a point in one time period. So this will be 1 by t. All right. Okay. Few other things. The maximum displacement of any particle is called its amplitude, denoted by a A. Okay. When we write the function y equals f ax minus bt, this is the y that we are talking about. So at any x, if this is at a distance x from the origin, then the disturbance can be calculated. The value of y can be calculated if you put the point in question where we are examining the disturbance and the time. So because this is at some time t1, we can just put t1 in this equation and find out what is the disturbance there. All right? Okay. Now, harmonic wave equation is one of the solutions of this partial differential equation where each particle is doing a simple harmonic motion. So we remember simple harmonic motion, this is the motion of one particle. Okay, this is not a wave, this is a motion of one particle. We remember that the motion of one particle is given by something like a sine omega t. Maybe we have a initial phase omega t plus theta. This is the equation of simple harmonic motion of one particle. See, there is no x in this. Okay. Now, harmonic wave equation is one in which all particles do simple harmonic motion. Okay. That equation is something like this: y equals a sine omega t plus minus kx plus phi. Okay. If we take minus, then the wave is traveling in the positive x direction. If both have the same signs, then the wave is traveling in the negative x direction. This is the generic wave equation of a wave when each particle is doing a simple harmonic motion. All right. Okay. So in this, we can see A is the amplitude. What is V? Velocity of the wave is the coefficient of t, omega, divided by coefficient of x. So omega by k is the wave velocity. Okay. What is omega? Omega is 2 pi by t, where t is the time period. What is k? K is also called the wave number, which is 2 pi by lambda, where lambda is the wavelength. Okay. Next, we will look at how we can derive the harmonic wave equation from simple harmonic motion of one particle. Okay, let's come back to the situation where we are creating some waves on a string. Okay, so here is the disturbance and this is the length of the string. Okay, and let's say a disturbance was created like this, which moved along. Okay, so at x equals 0, this is the what I would call the source particle, because we are creating the wave from the source particle. All the following particles, Okay, so for x greater than 0, all the falling particles, they copy the behavior of the source particle. So if the source particle is oscillating, okay, remember the particle is not moving, the particle is in its own position, but it is oscillating. And let's say the source particle is executing a simple harmonic motion. All the falling particles will copy the behavior, which is the simple harmonic motion of the source particle after a certain time. What time will that be? That will depend on the wave velocity. So the faster the wave is moving, quicker the falling particles will copy the behavior of the source particle. So it's easiest to start with the source particle. Let's try to write the equation of the disturbance of just the source particle. Okay? So we can write, since the source particle executes SHM, we can write Y0, denoting this is the disturbance of the source particle, as something like A sine omega t. Okay, and since I am showing that this is starting at equilibrium position at time t equals 0, so my phase, let's say, was theta. Here we are assuming that theta is 0. Okay, the wave could also have started from here. In that case, theta will be something else. But let's say in this case, theta is 0. So y0 we can write as A sine omega t. What is this? This is the equation of simple harmonic motion. Remember, this is not a wave equation. This is just the equation of the oscillation of the source particle. Okay? The wave equation will be something like y equals function of x comma t. We don't know what that function is. But when I put x equals 0, then we can represent y as this function of 0 comma t. That is nothing but this. Okay, so this is the wave equation, but this is the equation of the source particle's oscillation. All right. Okay, next let's take some particle at point P which is at a distance x from the source particle. Okay. Okay. Now remember, what is the definition of a wave? A wave is where a disturbance moves ahead with time. So the disturbance, when it has reached P, at some past time, it was at position O. Let me repeat that one more time. The disturbance that has reached P, that disturbance was at a past time at position O. Okay. So how long ago was at that position O? So that time we can find out by the wave velocity. So that will be x divided by v. In other words, we can say this is the time a disturbance took to reach from O to the point P. Okay. So now if I have to write the disturbance of point P, so let's denote by yp at some time t, can we say that is same as the disturbance at point O at a time t minus x by v? Because that disturbance took x by v time to move from O to P. It was the same disturbance that was at O at time t minus x by v. Okay. So if you have understood that, we can replace the function here. Y0 is given by A sine omega t, A sine omega t, and t we replace by t minus x by v. Okay. So what is this? this is yp. Now, if p is any generic point, then we can just drop the subscript. Let's say y of any point on the string is given by this equation. So then y becomes a sine omega t minus omega x by v. Okay? Okay? So this then becomes the generic equation of a plane progressive harmonic wave, or generic equation of a wave where each and every particle are exhibiting simple harmonic motion. Okay? We can further reduce this or simplify this in a different format. We can write this as y equals a sine omega is 2 pi by t times t minus omega is 2 pi by t x, and v is lambda by t, because v is the wave velocity, distance traveled in one time period divided by time period. Okay, so t gets cancelled. So we get this as a sine 2 pi by t minus 2 pi by lambda x. Okay, this we can also write in a little different format. If I take 2 pi common, t by t minus x by lambda. This is another way where we can write the generic wave equation of a harmonic wave. All right. Another thing is 2 pi by t is nothing but omega, and 2 pi by lambda is k, which is the wave number. So we can also write this as y equals a sine omega t minus kx. Now you can see that we got a minus here. The reason being, we assume that the wave is moving in the positive x direction. Therefore, we got a different signs for t and x. Okay. Now, if we had assumed that there is an initial phase, then more generic equation of a harmonic wave would be y equals a sine omega t minus kx plus phi, where phi is the initial phase. All right. Okay. One other thing, everything in this bracket is called phase, and phi is called the initial phase at x equals 0. Now this form, we can replace sine with cos. It means the same thing. It's just a difference in the initial phase. Okay. So any form of these, y equals a sine omega t plus minus kx plus phi, this is a harmonic wave. We could have y equals a cos omega t plus minus kx plus phi. This is also a harmonic wave. Okay, doesn't matter sine or cos. Okay, because sine and cos can be interchanged, only the initial phase will change. So this is the generic equation or form of a plane progressive harmonic wave, and you understand that it can be represented in sine or cos form, doesn't matter. A is the amplitude, omega is 2 pi by time period, k is 2 pi by lambda, and phi is the initial phase of the source particle. Okay. Now, if a wave equation is given like this, we can find out amplitude easily. What is amplitude? Amplitude is maximum value of y. What could be the maximum value of y is a. We can find out wave length. Wavelength is lambda. We know k is 2 pi by lambda. So lambda will be 2 pi by k. Okay. We can find out time period of the wave, which is, we know omega is 2 pi by t. So t is 2 pi by omega. We can find out the velocity of the wave, which is coefficient of t divided by coefficient of x. Also, you can think like lambda by t. So that becomes omega by k. All right. You can also determine the velocity of a particle, not the velocity of the wave. Velocity of the wave is given by this. Let me clarify. This is velocity of wave or wave velocity. But velocity of particle, how can we find out? If we differentiate y with respect to t, we can find out the velocity of the particle. If we differentiate it one more time, we find the acceleration of the particle. So all of that we can find out, okay? And once you substitute the value of x, we know the velocity and acceleration or the displacement of any point on that string, okay, at any time. All right. So the generic equation of a harmonic wave is a sine omega t plus minus kx plus phi. Okay. Now, if we have to find the velocity of a particle, then velocity of a particle, we can differentiate this by t with respect to t. So then the velocity of the particle becomes what? A omega a cos omega t plus minus kx plus phi. So differentiation of sine is cos, and then we go inside and differentiate with respect to t, so omega comes out. Okay. Similarly, acceleration of the particle is what? It will be d square y dt square. So we differentiate it one more time with respect to t. So this time it becomes, so cos will be minus sine omega t plus minus kx plus phi. So minus, and we had omega a and we get another omega. So omega square a. Okay. From this, if I ask you what is the maximum velocity of a particle, what will that be? So Vp max. So maximum value of cos is 1 is omega a. And if I ask you what's the maximum acceleration, Ap max, maximum value of sine is 1, so that's minus omega square a. These results are consistent with the maximum velocity in simple harmonic motion and maximum acceleration in simple harmonic motion, because you realize that this wave equation represents a wave which is harmonic wave, which means what? Each and every particle executes simple harmonic motion. Another important result we can get is particle velocity is negative of wave velocity times del y del x. And what is this? This is slope of yx graph or curve. Okay. This is an important result. Very useful result. You can of course find out particle velocity from here, but if yx graph is given, then it's easier to find the direction of particle velocity from this equation. Let me explain. Let's say we draw the plot of y versus x at some snapshot of a time. Okay, let's say the wave is like this. Okay, now if I want to find out particle velocity of this particle, okay, what do? I take the wave velocity, which is easy to get, it's omega by k from the wave equation, times the slope of the yx curve. So what would be the slope of the curve here? If I draw a tangent at this point, that is the slope of the curve. Now this tangent here is positive. So particle velocity, whether it is going up or going down, how can we find out? This is positive, wave velocity is this way, so negative means particle is going down. So whenever the slope is positive, the particle is actually moving in this direction. Up here, if I examine a point here, if I draw a slope, the slope is 0, so the particle velocity at this point is 0. Okay. Similarly, if I am examining a particle velocity here, what I would do is I would draw a tangent here. Now obviously this tangent, the slope is negative. So negative times negative is positive. So which means this particle velocity is here. These are all positive. Okay. In fact, here also it's positive. And when you come here, the velocity is 0. Okay. So this result is useful in figuring out which way the particles are moving. So again, when we come here, the slope is positive. So positive times negative is negative. So the particle velocities are downward. All the way up to this point where the particle velocity is 0 again. Okay. Now how can we prove this? Very simple. Let's do del y del x. Let's find that out. Del y del x. So if I differentiate it with respect to x, we have, let's just assume it is omega t minus kx. Okay, so let's write that down. Y equals a sine omega t minus kx. Okay, so del y del x will give me cos omega t minus kx. We have a here minus k. Okay, what is v? Or let's do what is vp. We found that relation here, it will be omega a cos omega t minus kx. Okay, if I divide this by this, or let's say we divide, this by this, so we get del y del x divided by vp. Cos and cos gets cancelled, a and a gets cancelled, minus k by w. Okay, or minus k by omega. So minus k by omega, we can write this as vp equals minus omega by k times del y del x. And what is omega by k? It is wave velocity times del y del x. Okay. So therefore, particle velocity is negative of wave velocity times del y del x. Okay. This is particularly useful to find the direction in which the particles are moving. Okay. Okay, another thing that we can see here, let's look at this acceleration of the particle. So, acceleration of the particle, we found that to be minus omega square a sine of this. Now, a sine omega t plus minus kx plus phi is nothing but y. So, this can be written as minus omega square y. Okay. Again, you see this is the condition for SHM. Okay. So, from this, another good observation we can put down, which is, let's say this is the y versus x graph. This is the snapshot. So, when y is positive, acceleration is negative. Okay. When y is negative, acceleration is positive. And that checks out with the condition for simple harmonic motion again. So, the acceleration is always towards the mean position. That's exactly what it is. Okay. So, now you know how to represent a plane progressive harmonic wave and how to interpret from the wave equation different things. And next is we will talk about the stuff in this bracket, which is phase and phase difference. Okay. So, we will discuss that in the next lecture, and we will also do some numericals along the way, so you get to practice what you have learned here. So, see you in the next one.